Section: Introduction. In this section, we discuss how recent studies have shown that allowing large language models, LLMs, to generate or search through intermediate steps before arriving at a final answer can enhance their performance on reasoning tasks. We recognize that giving LLMs the ability to adaptively allocate computational resources during generation can also lead to better outcomes within a fixed computational budget. However, many of these methods involve discrete intermediate outputs, making them challenging to train in a straightforward manner, and their additional computation occurs just in time during the output generation. We propose a different approach inspired by KV cache compression literature. Our method allows LLMs to reflect on their memories stored in the KV cache and transform these reflections into useful forms for future tasks. Specifically, we process the transformer's cache and enhance it with soft tokens generated in a single forward pass, rather than sequentially. This additional processing is handled by a separate model we call a coprocessor, while the base transformer remains unchanged. Once the KV cache is enhanced with the coprocessor's output, which we refer to as latent embeddings, the decoding continues as usual until the coprocessor is needed again. Our approach has several key benefits. 1. End-to-end differentiability. We enable backpropagation during coprocessor training, allowing for efficient optimization without relying on reinforcement learning. We use standard language modeling loss on pre-training data, making our method scalable. 2. Asynchronous operation. Since cache enhancement improves results for many tokens beyond the augmentation point and the base transformer stays unchanged during coprocessor training, we can operate the coprocessor asynchronously. This is different from existing methods that require sequential computation. We evaluate our method using Gemma 2 models trained on a diverse dataset. Our experiments show that without fine-tuning for specific tasks, our approach consistently boosts performance on various reasoning tasks. We found that increasing the number of latent embeddings generally improves results. For instance, we observed a 10.05% improvement on the GSM-8K task and a 4.70% improvement on MMLU when augmenting the Gemma 2-2B model with 64 latent embeddings. These findings highlight the potential of using KV cache coprocessing to enhance LLM capabilities. In our methodology, we enhance a frozen LLM by training a coprocessor that inputs a key value cache and adds soft tokens. We outline the architecture and training process of our approach. Our problem statement involves learning a coprocessor that takes the KV cache generated by the frozen LLM when processing an input and outputs a sequence of latent representations. The goal is to create latent embeddings that, when combined with the input, improve the LLM's ability to generate the correct output. Our model architecture enhances a frozen, pre-trained LLM with a coprocessor module that operates on the KV cache. The process unfolds in 3 stages. 1. KV cache generation. The input sequence is processed by the frozen LLM to create its KV cache, which contains the LLM's internal representations of the input, while the LLM's weights remain unchanged. 2. Augmentation. The KV cache is sent to the coprocessor, which has the same architecture as the pre-trained LLM. The coprocessor receives extra soft tokens that serve as abstract prompts and uses them along with the KV cache to produce latent embeddings. 3. LLM generation with augmented context. The latent embeddings are added to the original KV cache, which is then fed back into the frozen LLM. This enriched cache allows the LLM to generate the output based on both the original input and the coprocessor's output, enabling it to utilize the coprocessor's insights without needing to articulate intermediate steps. Training focuses on optimizing the coprocessor and its embeddings. The coprocessor shares the same architecture as the pre-trained LLM, and its weights are initialized from the LLM. We calculate the loss based on the final output and use backpropagation to update only the coprocessor's parameters. This targeted training allows for efficient fine-tuning without changing the pre-trained LLM. In practice, the coprocessor's augmentation can be done offline and asynchronously, potentially leading to improved efficiency and faster response times. Section Summary. In this section, we introduce a novel approach that enhances large language models, LLMs, by training a coprocessor to augment their key value cache with latent embeddings, allowing for improved reasoning without altering the frozen LLM. Our method enables end-to-end differentiability and asynchronous operation, leading to significant performance gains on reasoning tasks, as demonstrated by improvements in benchmarks like GSM-8K and MMLU. Section: Pre-training Setup. In this section, we describe our pre-training setup, which aims to help the coprocessor learn useful augmentations for predicting larger segments of text, not just the next token. We generate augmentations at multiple random positions within each text sequence, allowing the coprocessor to predict several tokens ahead. For example, given a sequence like A, B, C, D, E, F, we might randomly choose B and D as positions to augment. For each chosen position, the coprocessor creates a set number of latent embeddings in a single forward pass. Our goal is to predict a specified number of tokens beyond the augmentation point using these embeddings and the previous context. When B is selected, and we aim to predict 2 tokens ahead, the coprocessor uses the embeddings generated for B, along with the preceding text to predict C and D. This process helps the coprocessor learn to connect known context with future context through meaningful representations. Similarly, if D is chosen, it would predict E and F based on the embeddings for D and the preceding context. Our method is akin to the parallel decoding used in Quiet Star, but we generate latent embeddings instead of thoughts in token space, allowing for full differentiability while keeping the large language model, LLM, frozen. This frozen state enables asynchronous calls to the coprocessor, allowing its computations to run in parallel with the LLM's decoding without needing to insert between every token. We streamline our training by adjusting the input, attention mask, position index, and target to allow for a single forward pass. Instead of processing each augmentation position separately, we create an extended input sequence and attention mask that accommodates all selected positions. This setup allows us to compute the loss from all augmentation points simultaneously. We insert the generated latent embeddings into the input sequence after the corresponding tokens, followed by the tokens we aim to predict. The attention mask ensures that the original tokens can attend to all preceding tokens, while the latent embeddings and their corresponding tokens only attend to the original tokens before their insertion. The output from this process is used to calculate the loss and train the coprocessor. Our embeddings are designed to help predict future tokens, enabling a form of latent thinking that enhances the model's understanding of sequential dependencies in text, which is beneficial for downstream tasks. For our experiments, we validate our approach using the frozen Gemma 2.2b model. We train our augmented models, with only the coprocessor being trained, on a large dataset of 2 trillion tokens, primarily in English, which includes various sources like web documents and scientific articles. We conduct training for 100,000 steps with a batch size of 1024, using sequences of length 2048, 16 ahead tokens, and 128 randomly sampled augmentation positions. In our perplexity evaluation, we find that our augmented Gemma model achieves lower perplexity on the validation dataset compared to the pre-trained Gemma model, even for tokens beyond the number we defined during training. We generate latent embeddings after each token in the validation set and use them to enhance the cache for future token predictions. We measure the model's performance in predicting the first token after the embeddings and the 32nd token ahead, showing that our cache augmentation improves predictions even at greater distances. Our results indicate that augmenting the cache with the coprocessor enhances both short-range and long-range prediction accuracy. We observe consistent reductions in perplexity across different sizes of latent embeddings, confirming that our method improves the model's internal representations, leading to more accurate and coherent text generation. Section Summary. In this section, we describe our pre-training strategy that enables the coprocessor to learn useful text augmentations for predicting multiple future tokens by generating latent embeddings at various positions within a sequence. Our approach enhances the model's understanding of sequential dependencies, leading to improved perplexity scores on future token predictions, even beyond the training parameters. Section: Public Benchmark Evaluation. In this section, we evaluated cache augmentation using various public benchmarks that focus on natural language understanding and reasoning tasks. We only called the coprocessor once at the end of the prompt. Our method consistently outperformed the baseline frozen Gemma 2.2b model, especially on reasoning-heavy benchmarks. We observed a strong link between the number of latent embeddings and performance improvements in tasks like MMLU, GSM-8K, Trivia QA, NQ, and Math. For instance, on GSM-8K, accuracy increased from a gain of 1.29% with 4 latent embeddings to 10.05% with 64. Similarly, Math improved from a slight decrease of 0.12% with 4 to an increase of 2.06% with 64, and MMLU rose from 0.45% with 4 to 4.70% with 64. This trend indicates that more latent embeddings enable the model to engage in deeper reasoning, enhancing its capabilities. Other reasoning tasks, like ARC-E-C, Winagrande, and Bulk, also showed improvements with more latent embeddings. Although some tasks, such as Egival, BBH, and Human Eval, had less noticeable improvements or occasional dips with higher counts, our method still often provided benefits. This broad enhancement across various benchmarks highlights the effectiveness of cache augmentation for improving frozen language models. We also analyzed how our method scales with more training data and its adaptability to downstream tasks in the appendix. Next, we compared our approach with a similar baseline called the pause token method. Pause token adds trainable embeddings between the input and output sequences, prompting the model to think before generating output. The key difference is in how we generate latent embeddings. While pause token uses fixed, pre-trained embeddings that don't adapt to the input, our method generates dynamic, context-sensitive embeddings based on the input. This allows us to customize the latent representations, potentially improving reasoning. We directly compared the performance of the baseline Gemma 2.2b model with both pause token and our method, using 32 embeddings. Our method achieved a perplexity of 10.60 for the first token prediction, which is significantly lower than the baseline and pause token. Additionally, we reached an accuracy of 26.76% on the GSM-8K dataset, outperforming both the baseline and pause token. These results emphasize the effectiveness of our dynamic embeddings, which offer a richer representation than the fixed embeddings in pause token. We also viewed our technique as a form of latent chain of thought, COT, prompting and compared it to standard zero-shot COT, which adds, let's think step by step, to the input. While zero-shot COT can be useful, it requires the model to generate reasoning steps one token at a time, which can be resource-intensive. In contrast, our method generates latent embeddings in a single forward pass, making it potentially more efficient. We presented accuracy results for the baseline Gemma 2.2b model, zero-shot COT, and our method with 16 and 32 latent embeddings. Our method showed clear improvements, achieving 24.72% accuracy with 16 embeddings and 26.76% with 32, surpassing both the baseline and zero-shot COT. This suggests that our learned, context-sensitive embeddings provide a more efficient way to guide reasoning compared to the generic prompt and sequential token generation of zero-shot COT. We also explored different configurations for our coprocessor to understand the impact of design choices. Our default setup involved fine-tuning the pre-trained LLM as the coprocessor. We also tested training the coprocessor from scratch, which improved performance on all tasks compared to the baseline, but fine-tuning from pre-trained weights yielded even better results. This indicates that the coprocessor benefits from the foundational knowledge of the pre-trained LLM. We illustrated this improvement in GSM 8K accuracy as the number of latent embeddings increased, with the fine-tuned model consistently outperforming the one trained from scratch. Additionally, we examined the effectiveness of low-rank adaptation, LoRa, for tuning the coprocessor. LoRa freezes the pre-trained model weights and introduces trainable matrices, significantly reducing the number of parameters. We tested LoRa with ranks of 64 and 128, comparing their performance on GSM 8K to the baseline, the from-scratch training, and our fully fine-tuned coprocessor. LoRa with rank 64 achieved an accuracy of 23.35%, while rank 128 reached 24.03%. These results, while not as strong as the 26.76% from full fine-tuning, still represent a notable improvement over the baseline and highlight LoRa's potential for efficient training in memory-constrained environments. Lastly, we experimented with using the last layer's activations from the frozen LLM instead of the KV cache as input to the coprocessor. This approach, using 32 latent embeddings, resulted in a perplexity of 10.81 and an accuracy of 23.20% on GSM 8K, both of which were worse than the KV cache augmentation results. We believe that the last layer's activations do not provide as rich a representation for the coprocessor as the information from multiple layers in the KV cache, which negatively impacts both next token prediction and reasoning ability. Section Summary. In this section, we evaluated our cache augmentation method across various public benchmarks, finding consistent performance improvements over the baseline model, especially in reasoning tasks, where more latent embeddings significantly enhanced accuracy. We also compared our approach to the pause token method and zero-shot chain of thought prompting, demonstrating that our dynamic, context-dependent embeddings lead to better reasoning efficiency and effectiveness. Section: Impact of the number of ahead token in training. In this section, we explore the effects of changing the number of ahead tokens, which are the future tokens our model predicts during training. We found that while using more ahead tokens can improve the model's performance on later tokens, it can also make it harder for earlier tokens. Although adjusting the learning rate might help, we decided to use 16 ahead tokens for most of our experiments due to its strong results on the GSM 8K dataset. Next, we discuss chain of thought reasoning in large language models, LLMs. We noticed that standard prompting often fails to elicit complex reasoning, leading us to investigate prompting strategies that encourage intermediate reasoning steps. Chain of thought prompting has shown to significantly enhance reasoning by guiding LLMs to think step by step. Further research has looked into zero-shot chain of thought, combining multiple reasoning paths, and using reinforcement learning to optimize reasoning based on accuracy. However, these methods can be limited by natural language expressiveness and can be computationally intensive. We also examined latent space reasoning, where previous studies have shown that LLMs can utilize latent computations for reasoning tasks. We found that the middle layers of LLMs create interpretable embeddings that represent potential answers for complex queries. To enhance this latent reasoning, researchers have suggested adding meta tokens. The pause token method, which is similar to our approach, uses trainable embeddings to promote latent thinking. Unlike previous studies that rely on pre-trained embeddings, we generate latent tokens dynamically based on the input. Recently, Coconut introduced a new reasoning method using ILM's hidden states as input embeddings, but our approach focuses solely on training the coprocessor, making it more broadly applicable. We then address KV cache compression, a technique aimed at reducing the size of the memory that stores past activations for better efficiency. Some researchers have proposed using an in-context autoencoder to create concise embeddings for the KV cache. Our approach, however, differs as we aim to enhance the KV cache with latent embeddings from an offline coprocessor, improving the transformer's reasoning without altering its structure. This method allows for better decoding and performance in reasoning tasks, inspired by the idea of deliberation, where the coprocessor processes the KV cache to generate useful embeddings. Lastly, we look at augmenting LLMs with external modules to boost efficiency and performance. Various parameter-efficient fine-tuning methods have been explored, including adapters and techniques like LoRa that improve efficiency. Recent work has also focused on adding modules specifically for reasoning, such as COM, which enhances model capabilities through cross-attention. Our work shares similarities with hypernetworks, where one network generates parameters for another. In our case, the coprocessor acts as a hypernetwork, generating latent embeddings based on the KV cache of the frozen LLM. This allows for dynamic output generation tailored to the context, with the KV cache providing a rich representation of the input sequence.